Yeah, thanks, Mr. Chairman, and welcome everybody to this presentation about our design of a harmonic radar sensor. Yeah, starting with an outline, I will give a short introduction to the topic and then go over to the working principle and the setup of the design sensor. I will present wireless measurements, measurement results, and give a short conclusion and outlook in the end. Yeah, in the last years or decades, we have seen that process monitoring and process control became a very hot topic. I mean, we have more and more sensors that perform process monitoring and control tasks or support these tasks. And I mean, this is probably the main reason why we are all here for the Sensors Conference. Yeah, we see it in different environments or in different application scenarios, in logistics and fabrication, etc. And we also see that often for sensors, very specific requirements are existing or are demanded. And for some specific requirements, chipless sensors are researched and to meet these requirements. These requirements can be, on the one hand, low cost, or they could be that the sensor is supposed to operate in harsh environments. Harsh environments can be, for example, environments where it's very hot, let's say above 200 degrees Celsius, and then the intrinsic temperature limit of most silicon-based semiconductors cannot operate. So what is a chipless sensor? This is what's more or less categorized on the right. This is the wireless sensor. It's passive, that is, the sensor itself, the sensor tag, does not have a battery, but it also does not have any means of energy harvesting. It's chipless, that is, no integrated circuit, no semiconductor microchips on it. And yeah, due to this chipless design, then we avoid the necessity of having a semiconductor that must be able to operate at high temperatures. So then you might wonder, what is a quasi-chipless now? Well, in the design that I present now, we have an integrated circuit, a diode, a single unbiased diode, which is of course somehow a chip, but it's not operating in a digital way. It's just used as a nonlinear device. So we could replace it principally as any nonlinear device in the future, if we want. So this is, some people might argue, is not really chipless, but it has no energy harvesting, no battery, and is close to it, I would say. Yeah, but yeah, why do we go into a quasi-chipless system? This comes from the next and from the working principle in general of chipless systems. So a chipless system has a reader system on the one side, which is of course an active system, and it sends a radio wave towards a sensor, towards the tag, what we call usually tag. And the tag gives a backscatter signal. There is a passive reflection of the radio wave, so to say, of the wireless wave. And this reflection is similar to what a metal object might be. It's not identical, but very similar. And the reflection that goes back to the reader is first of all collected by the reader and is evaluated to gain information on the measurement value. But the tag or the sensor itself is not just alone in front of the reader. It's in an environment, and the environment might be metallic, might be dielectric or whatever, but it will probably cause reflections as well. And these reflections usually superimpose with the tag, and one task is then to split the tag signal, desired signal, from the unwanted environment signal. And the environment signal is usually called clutter, comes from radar clutter, and these clutter interferences are unwanted. So we came up with an idea, or there are a few ideas that use harmonic radar systems. And the harmonic radar systems makes advantage of the possibility to split the clutter signals and the desired tag signals in frequency domain. That is, in our case, we have the tag signal at the first harmonic frequency of the fundamental F1. So the clutter, of course, will be only at the F1 because it's not further processed, it's just a very passive or direct reflection. And it's at F1 because we're transmitting at the basic frequency F1 and at the reader. So this is one of the main advantages that we try to gain from the harmonic radar concept. Yeah, coming to the tag, it's placed here on the left side. It has mainly 4 elements, and I will come to these elements afterwards, just now. But just a general term, maybe we use, for all these 4 components, we use microstrip technology with quite principal printed circuit board technology. And we are operating with the fundamental at 1.55 gigahertz and the first harmonic then at at 3.1 gigahertz for the backscatter link. Yeah, coming to the tag components. First, we have two antennas on the tag, which are shown here. They have a gain of about, measured gain of about 5 to 5.5 dBi in the desired range. This is just one antenna that we measured. This is the smaller one for the backscatter link. But the big one looks very similar because the design is nearly identical. So it shows here in the desired range a nice gain in broadside direction. Then we have a temperature-dependent bandpass filter, and this filter has two microstrip lines here, which couple energy into a ceramic resonator, a dielectric resonator. And this ceramic resonator generates the transmission characteristic, which is a bandpass. So the bandpass is here, is a sharp peak that gives transmission, and we have no transmission for nearly all other frequencies. So another property of this resonator is that the permittivity epsilon r changes a bit when the temperature changes. And as the temperature changes and the permittivity changes, this peak will move to higher frequencies. Or as the epsilon r decreases, the peak and the resonant frequency will increase. This is what we will use, and we will see later. Then the next elements, or three elements, are the harmonic generator. This is the diode here, the unbiased diode, placed in a network of simple microstrip lines for matching purposes, to match to 50 ohm. Yeah, the harmonic generator has a measured gain of about minus 25 to 26 dB here at 3.1 gigahertz, or let's say it's actually a conversion loss of about 25 to 26 dB, or 27 dB. This is the loss that we have in order to come from the fundamental to the first harmonic, but this is the price more or less we have to pay. Yeah, the whole tag looks like this. So these are the module components. They're interconnected with simple SMA connectors, and this is how it looks like. The first antenna for receiving the filter here, the harmonic generator with the diode, with the small diode, and the backscatter antenna. Yeah, and these are the measurement that we performed. This is the setup. We have the tag mounted onto some metallic pipes here in our lab. We have a lot of metallic objects and some concrete walls and standing around. And on the right side, we have the reader, which is mainly a signal generator, a signal analyzer, and two antennas, one for transmit and one for reception. So, and then what we did we varied this distance between the reader system, or the reader antennas, and the tag, and we came to the following two examples of measurement curves. So when we see the received power over frequency over in the harmonic band, and we see that for 1 meter we have the blue curve, and the blue curve shows this sharp transmission peak which comes from the bandpass filter, which is desired. And as we increase the distance, the power drops, of course, because the free space path loss increases as the distance increases. But what we see is that the peak here is still recognizable, and is more or less actually very, very close to the same peak position over here. So the resonant frequency stays the same. And this is what we wish, and for the performance, of course, because as the temperature stays constant, we want to have the same resonant position. Yeah, we measured not only 1 and 3 meters, but up to 4.75 meters in 0.25 meter steps. And that's what you see here. The peak power of this peak plotted over the distance. I think this label is wrong, or not 100% right. Is the power Rx, the Rx power of the peak, and of course it drops as the distance increases. But we see that up to a distance of 3.25 meters, the signal to noise ratio, so this is the noise floor more or less down here, is higher than 17 dB. So this is quite nice. And only for higher distances we see that we have some sharp drops here of the Rx power, where we cannot detect the sensor anymore. These sharp drops are most probably caused due to multipass propagation. So if you remember, we have here with a lot of metallic objects in the hall and in the lab, and they cause multipass propagation effects. But up to a distance of 3.25 meters, the impact of these multipass is probably not very big. But for higher distances, it becomes evident. But this is a wireless operation. This is what nearly every wireless system has. But even for 4.75 meters, we see that the tag can still be clearly detected. Okay, yeah. The second setup, or a very similar setup, shows now the temperature measurements. We have now a constant distance of about 1.5 meters. And we see that the peak position, which starts at room temperature at about 3.12 gigahertz, shifts and increases to higher frequencies as the temperature increases. So we are here measuring up to 109 degrees in these first measurements, in this first proof of concept. So when we plot the resonant frequency, the FR, over temperature, we see this increase, which is approximately linear and has about a sensitivity, so a deviation of the resonant frequency of about 1.2 megahertz when we increase 1 Kelvin in temperature. Yeah, this correlates to a decrease of the permittivity of the dielectric resonator, so of this one, from 85 to 80 in this given temperature range, from room temperature to about 109 degrees. Yeah, coming to a conclusion. In the last minutes, I presented our design for a wireless temperature sensor which works quasi-chipless. It uses an unbiased diode to generate the harmonic and the temperature-dependent filter to generate the spectral characteristic and to gain the measurement value and to encode it and transmit it. The wireless indoor measurements have proved the concept. Up to 3.25 meters, we see a very clear detection of the arc signal of the sensor characteristic, and we can detect the room temperature. Not only the room temperature, but the ambient temperature of the tag. It shows a sensitivity of about 1.2 megahertz per Kelvin. As future work, we see a couple of improvements. First of all, the harmonic generator still has some optimization potential because the matching of the diode is not yet perfect. And on the other side, then probably size reduction and integration of the different components is a topic in order to have a small and compact sensor in the end. Yeah, then we also wish to increase the temperature range to really come into harsh environments, as I mentioned in the beginning. So example, having it operating at about 500 degrees Celsius or more. Yeah, that's it from my side. And yeah, any questions? Please go ahead.